Hey, how's it going? What the? Oh, that's weird. Hey.
I was wondering what do you teach?
What electives do I teach? I teach a lot of the computational classes. So the finite element courses, I teach those ones. So that's 410. This semester I'm teaching 417, which is called computational heat transfer. So it's almost like a kind of an extension of this class, but with MATLAB. What else do I teach? I have a biomedical course, which I teach this semester too, called, hang on a second. Okay, called EGME 442. And so that one is called computational cardiovascular biomechanics. And so basically we learn about kind of the fluid mechanics of blood flow. Yeah. So those are the main ones that I teach. A lot of those are in the spring. So unfortunately, those won't be offered again until next year. But 410 finite elements, I offered that in the fall last year, and so I think I should be teaching that in the fall this year.
Okay.
Yep. Yep. Hey, Stephen, can you hear me?
Hey, Doctor. Yeah, I can hear you good.
Okay. Yeah, and let's wait for the lecture to start, and then I'll give you the first 5 minutes.
I appreciate it. Thanks.
Yep.
How's your Wednesday going so far?
A little tough, honestly. I mean, this whole week's been a little bit tough. My cat might be passing away soon, so
Oh no.
she's she's had diabetes for the last 6 years, and it's catching up to her now. So yeah. She might be moving on soon, but
That's never fun. I'm sorry.
yeah. Hey guys.
Just a quick question. Am I going to be able to share my screen for everybody to
Yes,
see?
yeah. So I once the lecture starts, I have a couple announcements I want to make, and then I'll stop sharing mine, and then you can share your screen. All right, it's 2:30, so let's go and get started. All right, so good afternoon, everyone. How's everyone doing today? Good, good. Weather is been a crazy couple of days, but I guess that's how it is in California. All right, so to start the lecture today, we actually have a couple of special guests, and so we have someone here that's representing Titan Rocket that's going to tell you a little bit about that, and we have someone from the business school actually that's going to be telling you about a new initiative that he's going to be have in collaboration with the School of Engineering. Okay? So don't get too excited because I'm still lecturing today, and so you'll still have to hear me speak, but it's going to be after those two speakers. And so another announcement I want to make is I finally graded your homework 1, and so your grades for those should be on Canvas as well as my feedback. If you turn it into me in person, I have your homeworks here. You can pick it up after the class, and then I'll post the solutions later tonight as well. So unfortunately, I left the solutions back in my apartment, so I'll have to go back and get those. But as soon as I go back today, I'll scan them and upload them. Okay. All right, and so are there any questions before I hand it over to Stephen? Okay, all right, so let me go ahead and stop sharing my screen. All right, Stephen, so it's all yours.
Thanks, everybody. Thanks, Dr. Tran. You guys can see my screen all right?
Yep, you're good.
Okay, good. So I'm Stephen Sykes. I am the Vice President of Titan Rocket. I am just here to make a little announcement that we are kind of what our club is about and what we do as a whole. So we are a club for anybody interested in high-powered rocketry, anything from mostly amateur high-powered rocketry. If you ever bought those little kits when you were younger from like the hobby store or whatever to send a rocket up a few hundred feet or even maybe 1,000, we do that, but bigger. So we're first and foremost a senior design team. If you have thought about it at all, there's a senior design project coming up your senior year or your final year that you'll have to be a part of. You'll need to have a project to work on. We are one of those projects. We are what's considered a legacy project. which means that our club members who are a part of the club are usually the ones that are selected to become part of the next senior design team the following year. We are also in conjunction with a lot of other senior design teams, such as Titan Rover, Formula One race team, the Baja team, Titan Aero, Titan Sat. So there's a bunch of us, but not a lot of people know that legacy teams exist, and a lot of times they don't even know that they're going to have to select one their final year. So we want to give people the opportunity to understand that. The other thing that we do is something we call the Live, Laugh, Launch, which is basically for anybody that's not part of senior design. So you don't have to be an underclassman. You can also be a senior, but it basically means that we will work with you to understand what rockets are and all of the anatomy that goes into, developing those and stuff. So here's a few examples of a few of the rockets that we've personally built, with one of our team members last year launching for level 2 certification. We will help you order kits, put things together, understand how that works. Each member will learn more about the rocketry and what goes into that. It's not just a tube, fins, and something that goes high. There's a lot of science that goes into it. You'll learn about what the components do, why they actually do what they do. We can help out with learning more about CAD SolidWorks or any kind of CAD software. We also teach a little bit about the Open Rocket simulation software that can simulate our rocket and help you kind of in the aspect of designing and simulating how high or how far your rocket could go, which we used a lot for our design. As a senior design project, we use a lot of that software and the help of Dr. Mayoral here, who's in the plaid. He's the advisor for the senior design team, and he gives us kind of a guidance on how to properly engineer design using heat transfer and fluids and kinematics and all of the classes that we've taken throughout the years that you have or will take. He gives guidance on how to utilize all of that, come up with the equations that prove that this is what you're going to do. It's a really nice check on your resume as well. Last year's team was called Aphrodite. This year's team is called the Daedalus. And we launch high-powered rockets for this specific, Keystone Mechanical Engineering design project. We launch at Spaceport America Cup in New Mexico. It's a international competition of over 150 teams. There's also another one that's local called Friends of Amateur Rocketry. That one happens here in Mojave. We have design parameters that we have to meet, reports and different things we have to deliver to them. But essentially you and your team of 10 or so people will be working together to build that. The team's broken down into sub teams. The airframe team obviously deals with the whole body of the rocket. It's the overall structure, nose, fins, and different material selections for those. You deal mainly with the stabilization and the balance of the rocket. You got to fit all the sub teams inside the rocket, and everything's got to be balanced properly so that the rocket doesn't become a missile and accidentally skewer people's cars, which has been known to happen in the past. The Avionics Sub Team is the brain. It's the central nervous system, if you will. It basically deals with all of the flight computers, the altimeters. It tells us when to launch the payload, when to launch the recovery parachutes. It tells us how high we are and reads a lot of barometric sensors, gyroscopes, and other things. It adheres to all the competition rules, and you get to play with how many systems you use, redundancies, and a little bit of intro to programming with that. Payload is the most independent sub-team. You get basically free range to put whatever kind of payload in the rocket you can fit. Last year did a glider that had a slip wing design that would fit nicely into our airframe and then spring out once it was deployed. And then this year we're doing a self-stabilizing CubeSat that will have a CO2 canister like you see here with a bunch of thrusters that will reorient the payload as it falls. It just has to be like 8.8 pounds. It could be also a scientific experiment, so you could go talk to some people at the natural sciences and physics or even biology departments to do that kind of experiment stuff if you want as well. The propulsion sub team is obviously responsible for getting us up to altitude. We're trying to get to 10,000 feet. So this sub team had to design a way to hold the motor in the airframe so that it doesn't blast through and destroy your rocket. Motor selection is really important because we need to hit exactly 10,000 feet for full points. If we go over or under, we lose those kind of points. But you go through a lot of math, especially heat transfer and different fluids, in order to figure out how hot it's going to be, how much heat's going to transfer out to the airframe. Is it going to melt your rocket? It's a pretty important team. Recovery is our last team. These guys are obviously how we get our stuff back safely. I mean, it's the biggest part of the competition is being able to recover your rocket. So we don't land fancy like SpaceX, but we do use parachutes in order to slow our descent to a safe speed. And this is a picture of, in the upper right is the a servo connected to a CO2 canister that will help deploy and separate our rocket. And we have redundancies for everything. So this little brown cylinder that you see on the bottom right, that's the black powder charge, which is our backup. We're currently looking for the next team for next year. We submit names to Dr. Mayoral, who's our advisor, and we give him kind of a list of people who are interested and want to join. Ultimately, the department decides how many people are allowed on the team. Last year, they made the decision that only 10 people could do it. If there's more and more interest, they may add a few extra spots. We have currently a ECS welcome fair coming up next week on the 24th. So anybody that's interested could come check out our table, come ask us questions, come find us in E21, and that's our senior design shop. Come ask us questions, find out what would be a good fit. If you want to be interested in it, you can get started early. We encourage people to be a part of the Live, Laugh, Launch so that we can kind of give you a lot of information on how to build, how to do different things. And then when it comes your turn for senior design, you've got a project you're already kind of well known about, and you don't go into it kind of blind. If anybody wants to join, we have our Discord that anybody is free to sign up for. We will start holding meetings and, kind of organizing rockets and stuff like that if people want to purchase their own and stuff like that. I'll also post one in the chat just for anybody who's online. Yeah, this is basically us. Come check us out at ECS Welcome Week next week. And yeah, if you guys have any questions, please ask us in the Discord or whatever. We're more than happy to help. Just at senior design team or SDT, we'll see what it is and help you out.
Great, thanks, Stephen. Yeah, Titan Rocket's a great club. I've worked with a lot of their students too, just through my elective courses too, and it's always really cool to see what they're working on. From my perspective, I wish I joined the Rocket Club when I was in college, because you'll learn very quickly that even if you work for like an aerospace company, Boeing's not going to be happy with you if you tell them you want to launch a rocket just for shits and giggles. And so this is kind of your one chance to be kind of part of that team and to really launch a rocket, because it's a lot more difficult to do it in the real world. So
one of the coolest things is one of our members on the avionics team went to a career fair over the weekend, and because he had been working with a little bit of the electronics as well as some of the mechanical stuff, he got offered a job on the spot. So he doesn't start until June, but he's guaranteed a job after graduation. And I know a lot of the SolidWorks and a lot of the stuff that they saw from him working on the team definitely led to them offering him a job. So yeah, it's immensely helpful.
Great. Yeah, thanks, Stephen. So yeah, if they have any questions, I guess they can reach out to you. Normally I would allow some questions, but we do have one more guest that's lined up. Right?
Yeah. I understand time constraints and stuff. So I appreciate the time, and we're around. You'll probably see us wearing our shirts and stuff. So come out and holler at us if you need to. Thanks,
Great.
Dr.
Great. Thanks, Stephen. All right. And so our next guest today is someone from the business school. So we have Professor Opsfeld. Am I pronouncing that correctly?
You're doing great. That's perfect.
Great. Awesome. So he's going to tell you about a new initiative that we have going on in collaboration between the engineering school and the business school. So I'll leave it to him.
Excellent. So Justin, you're so on top of it. I didn't even notice that you had already given me permission. So that's cool. Thank you for that. So yeah, I am a professor in the business school. I'm going to talk to you about something called the Social Capital Academy. And this conversation you just had with Stephen Sykes is exactly sort of the point. It kind of is like, what's that informal, quote unquote, unofficial stuff, but it turns out to be more important, that makes the difference. And when you get involved in a team designing rockets, or you're involved in an internship, it's not just that you're getting a contact to someone who has an opportunity, but you're actually learning stuff about where to position yourself, how things interact with each other. And then when you're having that conversation with someone who's an employer potentially, you're smarter about where you want to be and what you can contribute in addition to stuff that you actually learn. And it's all that informal stuff that doesn't have a course that I want to get after in this thing I created called Social Capital Academy. So I'm a professor at the business school. I study social networks. My dependent variable is innovation. And so I'm like well known for work with respect to networks and innovation. And so to that point, and let me just double check. Justin, you can see the slides. I always like to do a double check there.
Yep. Yeah, we can see it. Just,
Good. So I spent over a year and a half, thousands of hours studying the automotive design process. I studied engineers. And so this is sort of a progression from a designer's sketch to the automotive vehicle that was the first to do three-dimensional design, as far as we could tell, anywhere in the world. So airlines and jet design did 3D sooner, but I watched that. I did some qualitative ethnographic work, and I also did a regressions to understand across a large division and 75 innovations who contributed to innovation. Turns out this informal stuff around networks were statistically significant in terms of predicting who was making a major contribution in initiating new innovations on the automotive platform. That got published in one of the best journals in the field. I wrote a book on it, Stanford University Press, and you could say that that's the punchline for this whole thing called Social Capital Academy. Like, you don't know what it is yet, but I'll just say the formula kind of goes like this, oversimplified. You're learning stuff in this class with Justin and in all these other classes. You get a degree. That all comes under the rubric of human capital. We know we all want that dependent variable professional success. And so there's a multiplier in here, and it's social capital. This is a network that you have, and how to work within it makes a huge difference in finding your way to a good job and doing well once you get there. And that was a significant finding, 0.001, that people had a certain kind of network and a way of engaging that network in an ordered logit model in my study, were super successful in creating innovation. Now let's pin this down in terms of Social Capital Academy. If you're sitting here like me, you're saying, okay, tell us what it is. So it's 4 2.5-hour modules. It starts on February 26th, and they're Saturday, just to be full disclosure, 9 to 11:30 on a Tuesday. In February, March, April, and May. And you need to commit to all 4. And here are what the 4 modules look like. The first is you work on your life story and your practical and personal life experience. And you do get paired within a team of 5 people like yourself. This will be engineering specific, not just generalists from different schools. And we're going to have 2 mentors with professional experience. I'll say more about that in a second, in the engineering space. And they're going to hang with you. Most of the 2.5 hours is you hanging and talking about and figuring out what your story is, what your strengths are, what are your challenges, and how to kind of get clear about how to use that to position to an employer. The second module, the second step here, is in how do you very explicitly start to figure out, how do I hang and talk with an employer? How do I introduce myself? How do I ask good, technically astute questions? And how can I take those things from my life story and make them useful? Because an employer is going to look at your GPA, and they're going to look at what you know how to model, but they're going to also want to know, are you the kind of person I want to work with in a team? And when you come out of module 2, you're going to have a lot more chops on how to do that. The module 3, which often gets a lot of attention, is we're going to introduce you to professionals in the engineering environment. And I'll say more about that in a second. You're going to meet 2 in module 3. You're going to have an option to meet with all of them, and optional meetings will schedule on Zoom. And the 4th is you're going to do some planning. Like, what am I going to do between now and graduation? So we don't target this for seniors going to graduate in 4 weeks. We're targeting juniors who can use this and parlay it for an internship, building out their network, and then ultimately build a robust campaign for searching for what I call career-related jobs. I call it career-related jobs because everyone's working. Most of you, like my students, are working, but are they jobs that lead the window to a really successful professional career? That's what you plan in module 4. Okay, just a few more slides here. So a little more in detail. So here are some of those 4 modules, 2.5 hours on a Saturday. you fill out this coat of arms and you just hang, you don't have to, no homework. You say, where was I? Someone did it on a tablet, which is what you're looking at here. Where was I when I was 10 years old, 5 years ago now? And also, where did I want to be 10 years in the future? You just draw in the space of the breakouts and you start to kind of figure out, here's some of the raw data that you can use and import into these conversations with professionals. That's module 1. You're going to be in teams of 5 with 2 mentors. The mentors have credentials like this. We have 15 lined up. We have over 25 across the 2 programs, one in the business and the engineering school, who are from Johnson & Johnson. And by the way, the reason they're here is because they want to meet you. You know, it's an issue of getting these scarce resources to each other. People actually want to hang with students and help them. They just don't know how to find you, and you don't know how to find them. So we have over 25 people from Johnson & Johnson, some on the East Coast and West Coast, that will be in this program with you. And you'll get 2 of folks like this as your mentors in your 5-person team during those 4 2.5-hour segments. Module 2 is this building social capital. If you're anything like my seniors, like I've taught over 1,000 seniors in the capstone course in strategy. I've taught MBAs at the best business schools in the country, and no one's got this stuff figured out. How to introduce yourself in an authentic way, that you're forceful, but humble. How to ask good questions is a skill. We get after that. And how to import something from your story that makes you distinct in the eyes of an employer. That's module 2. Module 3, we start to introduce you to professionals in your field. Another 2.5-hour sequence. You pick 2 areas. So a lot of you probably already committed to one of these 5, but it's custom to ECS. This is not like, painting and sculpture making. It's these 4 areas with respect to engineering. And then you will have one breakout with one person in one area and one breakout with a second person in another area of interest. And then all of those people will be available for optional additional 1-hour meetings where you can go and just talk to them. So here's an example of some of those people. These are already last semester signed up in the business school because IT, as you know, crosses over between business and engineering. So Larry Gray, data analytics, Alex Kaplan, world authority on blockchain and digital credentialing, knows the whole span of IT. Shana Chung at Johnson & Johnson, technology leader. And that's the example of the people that you will hang with. And then you'll have an option, for an example, in each of these cases to meet with these people after, where it's not a performance. It's like you hanging out and asking questions in a relaxed environment. This makes you smarter, obviously, for the career decisions and for your career searches. And then this is the planning session. This is a map we show people, but then you actually dig in that last 4th module and say, okay, where are the internships? If it's anything like the business school, my students don't figure out internships till it's too late. Where are the internships? How can I start to build my network? Who can I connect to on LinkedIn and get informational interviews? You can get the headline on that, but the actual practices to make that happens, planning that is in module 4. This is the design team. These are folks that are all involved. They'll be there. I will be there for every minute of the session. So it's not like I'm outsourcing this to someone else, but we have all these cool people. We have 15 mentors, and we're going to have probably 20 we pilot on, as I said, the 26th, and we're going to have another probably 10 or more career experts in module 3. Final slide. So here are those dates. You get a survey that we take because we have a rigorous pre and post test to evaluate the success, actually a control group as well. And you get $50 if you take the pre-test and show up on module 1. Then you take 2, 3, and 4, and you finish, take the post-test, you get another $50. I know $100 is not going to rock your world, but it just says we value your presence. There are those follow-on meetings that are optional. The only thing we absolutely ask you to kind of deliver on is the 4 2.5-hour segments. Invitations have gone out. And if what you've heard here sounds interesting, you may have this invitation in your inbox. We already have about 40 enrollments. We're probably going to cut off at 50 to 52 because we got to make sure we have enough career mentors of the quality that we're looking for. So there's only a limited number of seats left. And if you got it, find it in your inbox, sign up, and you're in. If you were in the control group and all they said is just take a pre and post test and we'll give you $20, that's this fifth bullet point, email me and I will, I'll get you into the program. I'll get you an official invite and put you into the program. You can see my email. I'm going to send this deck to Justin. And we also have a website if you want to check that out. I think I'm going to have to stop the share. And then let's see if I can just bring it back. And Justin, just so you know, because you're like me, or professor, you want to get onto your program. So, but I'll just say that's the website. This is just a landing page right now that we've created, but you can find me this way too. If you hit contact, you go to my email. And so that's the drill. I'm going to stop that slide deck and I will get this deck in a PDF format to Justin. And let me just ask, does anyone have any questions right now before I take off into digital space?
Any questions for David here?
Shout out to Mario for the cool picture. Of
Hang on,
the-
Dave. We got one question from the live.
yeah.
audience. What was it again?
Do we have to pay $50 to take the survey, or do they give us $50 to take the survey?
So the question is, do they have to pay $50 or do you pay them $50?
Oh gosh, oh my God, no, we pay you. It's an incentive. I'll just tell you something, sidebar. I mean, if you went and looked, you'd see a whole backstory on LinkedIn. John Seeley Brown is giving us $45,000 so far. And he used to run Xerox PARC. He was around when some of the massive breakthroughs in information technology were created up in Palo Alto. He was on the board of directors of Amazon. He was on the board of directors of the MacArthur Foundation. He's in all our leadership meetings, and he's given us the money to kind of bootstrap. This is a startup, and you are the second pilot or beta. But the bottom line answer to the question is, you take the I'm so glad you asked, by the way. I got to get clear. So probably went too fast. But you take the pre-survey. It's a 15-minute survey. You come to module 1, and when you come to module 1, finish it, you get a $50 Amazon gift card. You take 2, 3, and 4, take the post-test, and you get another Amazon $50 gift card. And it's a real super rigorous statistical study to say, we want to prove, you guys are engineers, you work with data. We want to prove that it makes a difference. Our first analysis of the data set from the fall is it is making a difference. It's creating a lot more confidence and expertise around careers and how to manage your network. But we're going to look for behavioral variables later, like internships and employment. But thanks for that question. Any other questions before I take off?
One more question.
So this is mostly focused on juniors then?
So the question is this mostly focused for juniors?
It really is. Now, what I don't know from that question, is this person a senior or are they a sophomore?
He's a senior.
And how, I'm sorry, I know Justin, you need to get on, but how close is he or she to graduation?
So a few months.
He's graduating this summer.
Yeah, so it really would, I mean, I appreciate the interest, but we're really trying to, and by the way, from a design standpoint, we want to have a homogeneous set of participants to see all juniors, what helps. And so it's really built for a junior, first, second semester junior who's saying, I can parlay this into an internship. So that's our target group.
Great. Any more questions for David before he heads off? Okay, yeah, thanks, David. That was really awesome. So I just my 2 cents. So I think probably the number one question I get from our students is, how can we get an internship? And so, they do well in their classes, and it's programs like this. And so you sign up for a program like this, you learn these skills, you network, and that's how you can, just like Dave was saying,
Yeah.
parlay, the information that you're learning in the class into professional success.
Can I just say something, Justin? I really want to cover, I want to say, like, I taught MBAs at at UC Irvine and also at NYU. And they're different. This internship is super important. And I'll get my graduating seniors to say, I want to get an internship after I graduate. It's too late. And in some ways, it's on the institution to do a better job to let you know where those opportunities are. But if we can kind of create, like within Social Capital Academy, some of the places where you go for that information, it can make a huge difference. Internships take place all the time. They can happen after you graduate, but they can happen, in the summer, they can happen in the fall. And I personal recommendation is go slower towards graduation and lock in an internship that will credential you, then rush through with 6 classes a semester and finish breathlessly without those credentials. So the internship is super important. And a lot of our students in the business school, they miss it altogether.
Great insight. Yeah, thank you so much, David. That sounds
Okay,
awesome.
thanks, guys. Can I just say, well, everyone's off camera. I'm curious what level of interest there is, but we'll get after that. Appreciate the time, Justin. I'll send you a PDF, and if people have questions, just email them.
For sure. Yeah,
Okay.
I'll forward them your contact information and I'll send them the slides so they can take a look.
Thank you very much. Take care, guys.
Thanks.
Thank you.
All right. I got to start charging people for ad time on my lectures. Okay, so we're back, and so back to our regularly scheduled programming, and so you know, two great programs. I think again, my 2 cents. I think they both sound really great to me. I've known about Titan Rocket for a while, but this is the first time I've heard about the academy from the business school, and it sounds like a great program. It's something I wish I had when I was a student as well. So. I think something I would definitely recommend you guys look into. Okay, and so the plan for today is we're going to pick up where we left off, and so we were talking about fins. In fact, there was just one more last piece of the example that we were running through at the very end, and so I want to make sure I finish that. Next thing I want to talk about is how to evaluate fin performance. And so from a thermal engineering point of view, that's something that's good because you want to evaluate how well your fin is doing. Okay. And then from there, we're going to talk about 2D conductions. Okay, and so in other words, how do we kind of extend what we've learned so far about conduction to the multi-dimensional realm? Because so far we've only just done 1D. Okay, and so let me scroll back up here and look at the example. Okay, and so in this example here, we have a very long fin, right? And so it has a certain diameter and it has a certain base temperature. And all we've done so far was we've computed the temperature distribution in the fin, okay? And so remember the temperature distribution is given by our function phi of x, right? Where phi, remember this is defined as our excess temperature. In other words, remember the excess temperature is the temperature that's in excess of the surrounding fluid, okay? And so I think, for this one, since we assumed that the fin was very long, we kind of just plug things into the formula. Okay. The next thing we computed was the total amount of heat transfer from the fin, right? And so we have a formula for that as well, which we derived at the end of class last time. And just to kind of remind you, the kind of the logic behind this is that, the total amount of heat that leaves your fin, it has to pass through the base at one point. And so we can compute the conduction heat transfer through the base. That's going to tell us how much heat is leaving our fin overall. Okay. All right. And so the last part of this example that we didn't get to was a test of our assumption, right? And remember, the key assumption in doing all this fin analysis was that we were assuming that the fin was very long, right? And the question that I posed for this was, how long does the fin have to be in order to be considered very long? Okay. Okay. And so if you remember, the kind of the upshot or kind of the reason that we assume a fin is very long was that so that we can assume that the very tip of the fin is the same temperature as the fluid. Okay. Okay. In other words, we have this relationship, and so when we take the limit as x approaches the length of the fin, okay, then what we say is that the excess temperature at x is equal to L is going to be approximately 0. Okay. Right? Because remember, if the excess temperature is 0, that means the temperature of the fin itself minus the fluid temperature is 0. So that means they basically reach the same temperature, right? And so in other words, we want to find out, how long does x need to be in order to have this this kind of relationship, okay? Okay. And so let me go ahead and write down our temperature distribution from before, okay? Okay, and so our temperature distribution from before was, where was it? So our temperature distribution from before was 75 E the minus 21.08 X, okay? All right. And so to find the point where this approaches zero, we have to use a little bit of mathematics here. And so, what do we know about this function right here, the decaying exponential, right? We know that it decays exponentially, hence the name, right? But it never fully touches zero, right? Even if you have like a very large number in the exponent, you might get a very, very small number, but you're never going to get fully equal to zero, okay? And so we kind of have to arbitrarily cut this off at some point. Okay? Because if we solve for, and so let's say that we apply this equation directly. So let's say if we do 0 is equal to 75 e to the minus 21.08 x, right? And then we try to solve for x right here. We're never going to get anything because we're going to take the natural logarithm of 0, and natural logarithm of 0 is minus infinity, and so that's not going to work. Okay. And so we're theoretically speaking, we're never going to reach a point where the fin temperature reaches exactly the fluid one, but we can compute the amount of length that makes us get close enough. Okay. And so we're going to define close enough. I can spell. We're going to find close enough as 0.1 or 1% of the base temperature. Okay. In other words, we're going to compute the point. Compute the point where the temperature has fallen off by 99%. Okay. And so instead of setting the left-hand side equal to 0, what I'm going to do is I'm going to set the left-hand side equal to 0.01 multiplied by the base temperature here, which is 75. Okay. Okay. And so if we do this, this is going to be equal to 0.75, okay, is equal to 75 e to the minus 21.08 x. Right, and so in other words, we're going to compute the point where the difference in temperature between the two fluids is about 3/4 of a degree. Okay, so we're going to say that's close enough, and so because we're not going to go any further than that. Okay. All right, and so here we're going to solve for x. And so we're going to divide both sides by 75, and so we get 0.01 is equal to e to the minus 21.08 x. Okay. In order to get the exponent out, we're going to take the natural logarithm of both sides. Okay. And so we have ln of 0.01 is equal to minus 21.08 x. Okay. We divide both sides by negative 21.08, and so we get x is equal to ln of 0.01 divided by negative 21.08. Okay. You punch that into the calculator, and you get a length of about 0.22 meters. Okay. Okay, and so in other words, if we have this fin and it's at least 0.22 meters, then we say that our very long fin assumption is valid. Okay. Yep.
Is the base temperature heat or T?
So the base temperature in this case is the feet, because we're solving everything in terms of feet. And so I think the actual base temperature here was 100 degrees C, and then the fluid temperature was 25 degrees C. And so the base excess temperature was 75. Yeah. Mm-hmm. Question. Exactly, yeah. Yeah, and so if we have a fin that's 0.22 meters, then at the very tip, then the temperature is going to be around 25.75 degrees C. Yeah. Mhm. Okay.
Are on the left-hand side of our equation, it's always going to equate to 0.01 since both of them are base.
Right, yeah. So I mean, in this case, we use a cutoff of 1%, but that was fairly arbitrary too. So you can use, you can use up to like 5%, or you can do 0.1%, something like that. But yeah, these two are always going to cancel out, and so you can just put 0.01 or just whatever your cutoff is on that side of the equation. Okay. All right, and so that's how we check and see, we check and to see how good our assumptions are in that case. Okay. All right, so one last thing I want to talk about fins is regarding fin performance. Okay. Because what you'll see in practice is that when you're doing kind of the thermal design of a device, adding a fin is actually not a trivial thing. And so it might seem like it's kind of trivial, like you just add like a stick on the edge of your device, but that changes a lot of how the device works. And so it changes the shape factor, right? So it changes the geometry. It changes whether you can fit your device in a box or something, which is pretty important actually. And then there's also structural, and also, if it's like a rocket ship or something, it's going to affect like the drag properties of your device as well. And so, it's not a trivial thing. And so, if you are going to go through the trouble of adding a fin, you want to make sure that it's in other words, that it's worth it from a thermal perspective, right? And so, in other words, if you add the fin, you want to have an idea of how much more you're enhancing the heat transfer. Okay. Okay. And so I'm going to show you two situations here. And so I'm going to show you a situation with the fin and then without the fin. Okay. Okay. And so if you have a fin, you have a situation that looks like this. Okay. And so you have some kind of fluid flowing past it. So you have T infinity and you have H. Okay. You have the cross-sectional area, AC. Okay. And you have the excess temperature of the base, theta B. Okay. And let's look at that same section of wall, but let's say that we don't have a fin anymore. Okay. Right. And so this is the exact same wall. And so if we look at the spot where the fin would have been, okay, so we can kind of carve out the same area, right? And so this section of wall right here has the same cross-sectional area, AC. Okay. And then just like the fin case, we're also going to have a fluid that flows past it with a temperature and convection coefficient. Okay. Okay. And so one way that we can evaluate fin performance is to just simply take the ratio of the heat transfer in the left situation and the heat transfer in the right. Okay. And so kind of the word definition of effectiveness is heat transfer with fin divided by heat transfer without fin. Okay. And so in other words, you have a ratio, right? And so ideally, your ratio here should be above 1, right? Because let's say that, your fin, let's just say for kind of just for the sake of numbers, your fin has, it allows you to have 50% more heat transfer for that little area of space, right? And so if your fin allows for 50% more heat transfer, then your effectiveness is going to be 1.5, right? And so that tells you that you're enhancing the amount of heat transfer by 50%, okay? And so the way that we define this in terms of equations is that we have in the numerator, we have QF, okay, where QF is the total amount of heat transfer from the fin, which we defined at the very end of class last time, okay? And then we're going to divide it by the amount of heat transfer from this small slab right here, okay? And to compute the amount of heat transfer from this, we're going to use Newton's law of cooling. Okay? All right, and so Newton's law of cooling, we take the convection coefficient, we take the cross-sectional area of just that slice right there, so just AC. Okay. We do T base. Okay. And so we do H times AC times the temperature difference, which is T base minus T infinity. Okay. But we can put this T base minus T infinity in terms of theta, just because we're computing it anyway. And so one formula for the effectiveness is QF divided by HAC times theta B. And so this formula implements exactly what this definition for effectiveness is, okay? And in order for your fin to be effective, at the very least, it should be above 1. Do you guys have any questions back there?
Yeah, sorry, just wanted to pressure on the.
Okay, yeah, it's just the formula that we use to compute convection heat transfer from a surface. Yep. Mhm. So at the very least, effectiveness should be above 1, but certain situations will want higher effectivenesses, based on the application. So and so it depends on the application, but ideally, if you can get an effectiveness of 2, saying that your fin is twice as effective as as having no fin, that's usually pretty good. Okay. All right. And so, right. And so this is how you can compute how effective your fin is going to be. Okay. And so in the next homework assignment, I know everyone's working on homework 2, but in homework 3, I'm giving you a problem where I'm having you design your own fin. And so I'm going to give you a kind of a practical situation, and I'm going to say that part of your task as an engineer designing the system is you have to design a fin for this. And I'm going to give you 2 different designs. So I'm going to give one where I give you the cross section, and I'm going to have you compute the effectiveness of that. And then in the second part of the problem, you're going to change the cross section to make it more effective than the one I gave you. Okay. Okay. Any questions on this? Yep.
For the most part, fins are for cooling, correct?
Correct. Yes.
Are there any examples of the opposite?
I mean, yeah, I mean, theoretically, yeah, it's definitely possible. I can't think of a practical one at the moment. Maybe something in like the Antarctic or something like that, where you need to, heat something up very quickly. Then that's possible as well. Yeah. Mm-hmm. Question over here too. Okay. All right. And so that's fins. And so fins are fascinating because they seem like very simple devices, and so they're just literally a piece of material that's sticking out, but they're very useful in terms of their thermal properties. Okay, and so for the last 30 minutes today, I want to talk about 2D heat conduction. And I guess by extension 3D as well. So we'll lump them in. And so far, up to this point that we've covered so far, we've only just considered 1D situations, right? And so what I mean by 1D is that when we solve for the temperature distributions, whether it be T or recently until it was theta, right? These T's and these thetas were only functions of just one variable, right? And so we might have T of X, right? Theta of X, or if we're looking at radial cases, we have T of R, right? And so all of these only have one variable or one independent variable. Okay. And that basically allows us to solve our heat equations, because we end up getting ordinary differential equations. But for more complex cases, 2D and 3D, it becomes a bit more complicated. Okay? And so we can look at the full heat equation in 3D, so I can kind of show you what I mean. Okay? Let me show you the 3D version so that you can kind of appreciate the whole thing. Okay? And so in 3D, the heat equation is partial squared T, partial X squared plus partial squared T, partial Y squared plus partial squared T, partial Z squared plus Q dot over K is equal to 1 over alpha partial T partial little t. Okay. So I think previously, the only spatial derivative we had was just one of the x ones. But when you extend this to 3D, then you also have to have a derivative in the y direction and in the z. Okay. All right. So this is our heat equation. All right. And so even if we make the assumption that our situation is steady state, and so if we assume that this term is gone, like we usually do, we're still kind of screwed, because we have 3 independent variables here. Right? Okay. And so we can't solve this with just simple integration, just like we did before. Right? And so when you have a differential equation like this that depends on more than one variable, we call this a partial differential equation. Okay. Or in other words, they're called PDEs. Because partial differential equation is kind of a mouthful, so PDE is a little bit shorter to say. Okay. All right, and so most people, and I mean this quite literally, and probably 99.999% of the population does not know how to solve PDEs, and that includes most masters and doctoral people in engineering as well. And so it's hard to solve these things, and it's not an easy thing. And so to get solutions to this, you really kind of have two options. And so one option that you can do is you can solve this in a computer. And so we have a lot of great computational techniques out there, like finite elements, right? And so you can solve this in a software called like ANSYS. Okay, so that's one option. But if you don't have access to a computer, then you have to have other ways to do this. Okay? And so we're not going to go through the computer method. That's actually more of a subject of 417. I was actually talking with someone before the class about that course. And so if you are interested in computer solutions to this, I would recommend you take 417. Little self plug for myself there, but but we're going to go over the other method today. Okay. And so the other method that we're going to use is we're going to kind of piggyback off of the great work that other people have done. Okay. And so what I mean by that is that before the age of computers, scientists kind of looked at this equation and said, even though it's really hard, we can solve this solution in certain situations. Okay. Okay. And so in other words, people have actually put in the time to actually solve this temperature distribution for certain situations. Okay. And so what we can do then is that, knowing that people have solved this already in those situations, if we come across another situation that looks similar to something that's already been solved, we can just kind of, you know, we can basically kind of take their solution and apply it to our situation. Okay. Okay. All right, and so the way we actually do this is actually, you know, very, very simple, at least from a mathematical point of view. Okay, and so the way that we apply this is through a technique known as shape factors. Okay. Okay. And so the equation that we're going to use looks like this. Okay, so we're going to say that the heat transfer in a 2D or 3D situation is equal to S being the shape factor, multiplied by K, which is the thermal conductivity, multiplied by a temperature difference. Okay. Okay. And so this Q is heat transfer. This K here is thermal conductivity. Okay. S here is the shape factor. Okay. And of course, T1 minus T2 here is a temperature difference. All right. And so mathematically, you know, it looks pretty simple. It's not bad. And so, you know, we know what thermal conductivity is. And so, you know, we've already tabulated it and we've already used it a lot. Temperature difference, we obviously know what that is. Okay. The only thing that's new here is the shape factor. So this shape factor, the way we use this is that we basically look these up in a table. Okay. We look them up in a table for situations that look similar to our situation. Okay. And the idea behind the shape factor is that you can almost think of them as like a modifying factor that modifies the amount of heat transfer based on the 2D and 3D geometry. Okay. Okay. And so there's a table for this in your book. I also have an abbreviated version of it in the notes, which I'll show you in a bit. Okay. But basically, the way that you do this is that you look at a problem, you look at the geometry of the problem, and then you go to the table, and then you try to find the entry in the table that matches up to your situation as closely as possible, and then you're going to basically use their formula for the shape factor and compute that. Okay. It sounds like a lot of steps, but we'll do an example, and you'll see it's actually it's pretty straightforward. Okay, so actually, let me go ahead and show you that table before we move on. So I think it helps a lot. Okay, and so this is in the notes that I posted online. Okay, and so you don't have to copy this down because it's a lot to write down. But basically, the way it works like this. And so there's 4 columns to this table, and so you can see here that we have a column for the geometry, which is basically describes what the geometry is. Okay? And so if we look at the first row right here, the geometry is an isothermal sphere buried in a semi-infinite medium. Okay, and so that covers the case. Let's say that you took a the arc reactor in Iron Man. You buried it underground, and so this is how you would compute the heat transfer from that. Okay, The second column shows you a picture just so that you can kind of see, right? And so you can see from the picture on the first row that we have a sphere. It's at a certain temperature T1, and we have the ground, which is at a certain temperature T2, okay? And we also know the depth of the sphere, which is Z, as well as the diameter of the sphere D, okay? The third column will give you any restrictions. And so basically this condition has to be satisfied in order for you to use the equation, okay? And then in the last column there, that shows you the shape vector, okay? And so, right. And so this last column is basically an expression for what S is for that situation, okay? Okay, and so, you know, the way to kind of do these 2D problems is that you look at the situation, you compute the shape factor, and then you plug it into that equation that I showed previously to compute the heat transfer. Okay, any example or any questions on this before we do an example? Okay. Okay. All right. So let me go ahead and bring back the notes here. Okay. And so let's do an example just to kind of show you how this works. All right. And so in this example, let's say that we have a horizontal pipe that is 15 centimeters in diameter. Okay. And the length of the pipe is 4 meters. Okay. And we'll say that it's buried in the earth, and so it's buried underground at a depth of 20 centimeters. Okay. All right, and so visually it looks something like this. And so we have, you know, the earth right this, okay? And then underneath the earth, we have our pipe. Okay. And so the diameter of this pipe, the diameter, what do we say, it was 15 centimeters. Okay. The length of the pipe is 4 meters. And so basically you can think of it as extending into the page. This is 4 meters here, okay? And the depth, you know, basically from the surface of the earth down to the center of the pipe, we say this is 20 centimeters, okay? All right, and so the other piece of information we know from the problem is that the surface of the pipe is held at a constant temperature of 75 degrees C. And so T pipe is equal to 75 degrees C, okay? The other thing that we know is that the earth that surrounds it, and so, you know, all the dirt that's basically around the pipe, I guess we're like in Antarctica or something. So the T dirt is only 5 degrees C, okay? Right. And we also know the thermal conductivity of the dirt as well. Okay, so the thermal conductivity of the dirt is 0.8 watts per meter K. Okay. All right, so given this situation, what we're interested in computing is the heat loss from the pipe. Okay. Right, and so in other words, you know, we're interested in computing heat. All right. Any questions on this so far? All right, and so you know, this is an interesting situation because, you know, normally, you know, we have pipe, you know, which normally we associate with cylindrical coordinates, right? And so on first glance, you would think that, you know, maybe we can solve this with our cylindrical resistances that we've looked at before, right? The challenge with that is that this is kind of an asymmetric situation if you look at it, right? And so above the pipe, we know we have 20 centimeters of dirt above the pipe, okay? And then below the pipe, we actually have a lot more dirt. And so, we kind of have this, asymmetric situation where, the heat transfer that comes off of it. If I can get the orange here, okay. And so the heat transfer that comes off of it is not going to be completely radial. So, maybe we have more heat transfer, because in this case, I guess the dirt's really cold. Maybe we have more heat transfer. Maybe we have more heat transfer going down, okay, than we have coming up, okay. Right. And so because, we don't know how far down this dirt is going, we can't assume that our heat is going to be completely radial, okay. And so there's probably going to be some asymmetry to this. And so, because we have this dirt layer here, we're going to need to do this with using shape factors. Okay. All right, and so from before, we know that Q here is going to be equal to S times K times difference in temperature. And so the difference in temperature in this case is going to be T pipe minus T dirt. Okay. Right. Since this is a heat transfer to the dirt, then the thermal conductivity we're going to use here is that of the dirt. Okay. And so all these are given to us. And so the only thing that we don't have yet is the shape factor. Okay. Right. And so when we come across a situation like this, we are going to look in the table. Right. We're going to look in a table for a situation that looks similar to what we have here. Okay. Okay. And so you can either use the table in the notes. Okay. So I wrote down a lot of the table in there, but that table is not the full table. And so if you want the full table, you'll have to look in the textbook for it. Okay. But let me hop back to the notes so that we can kind of see. Okay. And let's look for an entry in this table that looks like, the situation that we have, right? And so the situation that we have is we have a pipe that's buried underneath the earth, right? And so are there any entries in this table that kind of matches up with that? 2, right? So the second one. So the second one is basically exactly what we're looking for. And to be honest, it better because this is an example from the textbook. So it should match exactly with something here. Okay. Okay. And so for 2, we have basically an isothermal cylinder buried underneath a semi-infinite medium. This one's interesting because we actually have two different paths that we can take, right? So we have 2 different shape factors, depending on certain conditions. Okay. And so one condition for both is that the length of the pipe has to be much greater than the diameter, right? And so if you remember from this problem, the length of our pipe was 4 meters and the diameter was 15 centimeters. Okay. Okay. And so if we compare 15 centimeters to 4 meters, then 4 meters is much bigger than 15 centimeters. Okay. And so this is going to be satisfied for both cases. Okay. The next condition that we have to check is we need to check. Oh, okay. Is we need to check the if the z is greater than 3d over 2. Okay. Our question. So do we have a table like this for solving fins? Not to my knowledge, no. And so at least in the version of the textbook that I have, there's no table for fins. Yeah. Okay. And so z here is, you can see from the image, is the depth that it's buried. Okay. And d is the diameter. Okay. Okay. And so if the depth is greater than 3d divided by 2, then we use the bottom formula. Okay. But if this is not satisfied, then we're going to use the top formula for the shape factor. Okay. So let's go ahead and compute that really quickly. And so we have Z, and so the depth in this case was 20 centimeters. Okay. Okay. And then we can compute 3D divided by 2. Okay. And so our D here is 15. And so 3 times 15 is 45. We divide that by 2 and we get 22.5 centimeters. Okay. And so what we have in this case is that the depth, Z, is actually less than 3D divided by 2, right? Because 3D divided by 2 is 22.5. Z, on the other hand, is 20. And so we're not going to use the bottom one. And so our formula for the shape factor is actually going to be this top one right here, which is 2 pi L divided by hyperbolic cosine of 2Z divided by D. Okay. All right. So does that make sense about why we chose that formula for the shape factor over the other one? Okay. Right. And so when you're using these shape factors, first of all, you have to find one that looks similar to to what you have. And then the other thing you have to account for is, if there are any restrictions, and make sure that you can satisfy those restrictions, in your problem. Okay. Okay. So let's go ahead and remember that equation. Let me clean up this PDF, because this is actually on Dropbox, and I don't want these notes on my PDF. Okay. And let's return back to our notes. Okay. And so with that knowledge, we know that S. Our formula for S is going to be 2 pi times L divided by hyperbolic cosine inverse of 2ZD, or 2Z divided by D. Okay. All right. And so we have everything here. Okay. So for the inverse hyperbolic cosine, you can just plug that into a graphing calculator or MATLAB or whatever your your calculator of choice is. And if we do all that, we end up with 15.35 meters. Okay. Okay. And so now that we have the shape factor, we can go ahead and plug it in here. We know the thermal conductivity. We know the temperature difference. And so we have everything that we need to compute Q. Okay. And so we have Q is equal to 15.35 meters times 0.8 watts per meter Kelvin times the temperature difference, which we have 75 degrees C minus 5 degrees C. Okay. You plug all that in, you get a heat loss of 859.6 watts. Okay. All right, and so that's the basics of how you do 2D conduction, or at least the level at which we're going to do in this class. Right? And so basically, you look at your situation, you try to find the shape factor that matches up with it. You compute that shape factor, and then you plug it into that heat transfer equation. All right, any questions on this?
Yeah, there's one in the chat.
Oh, there's one in the chat. Yeah, so I answered that one earlier. So there is no table like this for fins. And so the way we solve fins is basically use the fin heat equation that we did earlier. Okay. Mm-hmm. Okay. All right, and so there's one more thing, or one more concept that I want to give you guys before we part for this week. Okay. And that's actually with regards to this equation right here. Okay. Because we've actually seen an equation like this, actually many times before, right? So let me actually go ahead and write it down here again. Okay. And so we have Q is equal to SK divided by, or multiplied by, T1 minus T2. Okay. Let me do something like this. And so let me rearrange this equation just a little bit. Okay. And so instead of SK times T1 minus T2, we have T1 minus T2 divided by 1 divided by SK. Okay. So this is going to be equal Q. Right, so this is the exact same equation as the one on the left. I just kind of rearranged the terms a little bit. Okay. And so why did I do that? And so why did I bother to kind of put 1 over SK in the denominator? Okay. And so the reason I did that is to make it look like something that we've been working with, a lot this semester. Okay. And so if we think of our thermal circuits, right? Where we have temperature T1, temperature T2 separated by a resistance. We know that in situations like this, the heat transfer is equal to T1 minus T2 divided by the resistance, right? Where the resistance can take many different forms, depending on if it's a conductive resistance, right? Depending on if it's a convective resistance. Right? But the basic idea is that we take, if we have a thermal circuit like this, we take the difference in temperature between the two nodes, and we just divide it by the resistance in between them. Okay. Okay. And so if we look at these two equations, we can see that there's a lot of similarities, right? And so we have Q by itself on one side of the equation. We have a difference in temperature on top. Okay. And then we also have something in the denominator here as well. Okay. That conceptually kind of represent the same thing. Okay, and so one way that you can interpret the shape factor equations is to say that we can think of it in terms of a thermal circuit. Okay. Okay. And so in other words, we can have our 2D / 3D. Okay. I don't remember if there's any 3D cases. I don't think I have any 3D cases in my notes, but there might be some 3D cases in the table in the book. Okay. And so the thermal resistance of a 2D, 3D situation is just nothing more than just 1 divided by the shape factor multiplied by K. Okay. Right, and so that's another way that you can interpret shape factors. And this interpretation is important because in homework 3, I'm again going to give you a problem which is going to be 2D, where you're going to combine kind of this idea of a thermal resistance for shape factors together with other thermal circuits that we've looked at before, okay? And kind of in what I think is kind of a really interesting application there. All right, any final questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for. And so that wraps up 2D conduction. And so when we next time we meet, we're going to talk about transient conduction, which is conduction that changes with time. Okay. And remember, the next time that we're going to meet is next Wednesday, because Monday is a holiday, and so we're not going to have lectures. But since I do have, I know I did assign the homework to be due Monday. I will have office hours on Monday, and so I will be on in Zoom from 11 a.m. to 12 p.m. on Monday. So if you have any last second questions, you can come into the Zoom call and ask them. Okay. Oh, question. So most of the time I'm here physically as well, and so you can come to my office. Yes, yeah. So the syllabus has my office, but just this upcoming Monday I won't be here. But for Tuesday I have Monday, Tuesday, Thursday office hours, so I'm in my office physically. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your afternoon. Hope you guys enjoy your long weekend, and I'll see you next Wednesday. Thanks, guys. Yes. Oh, yeah, yeah. If you turned in your homework in person, then I have your returned ones here. There's only about 5 weeks, so. Yep.
I had a question about contact resistance.
Okay.
When we create the thermal circuit, is it in parallel?
It's in series.
It's in series.
Yes.
Okay, sure. And then how do we account for every single iteration
So the contact resistance, it's not like a really strictly measured thing.
Oh,
And so it's kind of meant to represent that when you're in two things contacting, that the overall effect is like an additional resistance. So this contact is like an average. Yep. Oh, it's over here. There's only two. Most people turn it on high.
Oh, gee, that's not, what time you say that What are you gonna do?
Luan, did you have any other questions before I wrap it up?
I sent
Nope.
you an email for the last lecture. Like I took a screenshot.
Wait, say again.
I sent you an email for the last lecture. I took a screenshot.
You took a screenshot? Oh, okay. Okay. Great. Okay. So I'll see you next week.
Thank you. Bye.
Yep. Hey, bye.